wanted to get your attention for a minute. Couple of things. So I pushed a little bit back from where I thought I would be at this point, just slightly, because I realized that we needed to have a lecture on reactors. It's important for multiple reasons. And actually, it really sets the stage beautifully for bombs. Okay, because reactors do the same thing that certain classes of weapons do. They just do it much more slowly and in a controlled way. Okay, so really all of the physics is the same. So that's what I'm going to be doing today. And with some luck, we might even start with weapons. And really, I can finish them because we've laid all the groundwork. I need one more lecture, and I'm sort of done with the fundamentals of weapons. You'll understand how they work. You'll be able to go out and say that you say that you know the fundamentals of it. Okay, and it helped to get some guidance from Earl, which I got to do last week, which was really good. Okay, so just to let you know, Sammy always has your back. She sends me these wonderful, detailed, long emails telling me about like kind of her experience interacting with all of you, which is terrific. And I think in office hours, which is really the best kind of interaction that you can have. And one of the things that happened in our last exchange is that I realized that maybe it wouldn't be a bad idea for me to have a sort of open-ended Q&A session on the technical material with anybody who's interested. Now, I learned when I first came to Cal and started teaching, I learned from Rick Norman that students always feel more comfortable with the GSI than they do with the professor. And he told me, you have to leave. For discussion sessions, you have to leave. You not be in the same room. So this is a little scary. I'm asking you to be in the same room with me. But really, I'm not frightening. And I wanted you to be able to ask questions, particularly folks who feel a bit more questioning about the technical material. But this is open to everyone in the class to participate in. So if there's very little interest, I may still do this, just because then it will be a better interaction. Okay? But let me just get a show of hands right now of everybody who's here. Who would be interested? And we still have the schedule. I've got 1 hand, 2 hands, 3, 4, 5. That's it makes it. That's enough. And so here's the deal though. If you raise your hand, this is an honor system, you get to email me and say kind of generally when you're available. If you didn't raise your hand, then I'll try to set a schedule based on the people who raise their hands, and then hopefully it'll work for you. I can't hold repeat sessions, but I can hold fun. And I'm willing to do things, by the way, on nights as well. Weekends, I mean, if it's really important, but nights are okay. All right. Okay. Lecturing, reactors into weapons. Okay, it's a horrible sounding thing. You know, it's actually very bad, perhaps from a public relations standpoint, because nuclear energy has tried so hard to divorce itself from the weapons connection. And they really are different. You cannot turn a reactor into a bomb. Full stop. Okay? But let's be honest also, the physics that's involved in it is essentially the same. Okay, so I mean, that's okay. I like to say that, you know, bullets killed by kinetic energy and cars work by kinetic energy, and yet we don't hold those kind of bolt contacts. So, one other thing, before I jump into the main part of this lecture, was that Sammy mentioned that there was some concern about temperature, because I keep shifting back and forth between temperature in units that you're used to thinking of it in, like degrees Celsius or degrees Kelvin, and energy, okay? Now, that's just because they really are just two different ways of looking at the same thing, okay? Temperature is a measurement of the most likely energy value for particles moving randomly in an environment. Actually, the $25,000 special word here you could use is something called stochastic, which is random but within a distribution, okay? So the air that's moving around in this room has a distribution of velocities, the air molecules. But I can describe that distribution with one number. It's kind of cool. You can think of it as an average. That's close enough for government work. It's not an average. It's actually slightly different than that. But it is a single number that represents that velocity. So it turns out that that velocity, if you were to look at the kinetic energy of the individual particles, it's going to be somewhere between 25 and 30 milli electron volts. That's 1,000th of an electron volt. Okay. An electron volt, again, is the energy that an electron would get getting accelerated across a 1 volt potential. You know, if you have 9 volt batteries, this is 1/9 of that. So, in other words, the air is not moving very fast in this room. The energy density in it is extremely low. 1 volt is like the surface of the sun. Okay, just to give you an idea. 5 to 10 kilovolts, so that energy again, about 25 millieV. So that's about 300 Kelvin. Sorry, that should be 27 degrees, not 27 degrees. That's right. I did get an option. Okay. 27 degrees centigrade. Okay. The core of the sun, it's actually 5 to 10 kilovolts. That's weapons thermal. Okay. And that's the temperature inside of a weapon during the immediate aftermath of it going off. Okay. It's actually slightly, 5 to 10 kilovolts is slightly higher than the temperature at the core of the sun. But it's typical of stellar interiors. And the one that I like to remember is just at 86 kilovolts or 87 kilovolts is about 1 billion degrees. Okay, that's the temperature in a supernova, which is the hottest environment or largest scale explosion really that we've seen so far in nature. Okay, this just gives you the full range of where things go. And of course, 0 is 0, absolute 0. Okay. So we go from about 2 degrees Kelvin as an average, the minimum energy sort of in the universe as a residual from the Big Bang, up to about 1 billion. Of course, you could go higher, but that really doesn't happen in any sustained way for us. So if you want to remember anything from here, I like to say 86 kilovolts is 1 billion degrees, which means that 43 kilovolts, half of that would be how much? Half of it. That's it. That's it. Enough said. All right, what comes out of fission? Remember this table? I have a list of all the things that come out. The big focus here was on the 200 MeV total energy output. Okay, most of that is in the form of the fragments. And of course, for a reactor for energy production purposes, or for a weapon for energy production purposes, the fission fragment kinetic energy is kind of the most important thing. And all that energy is rendered up locally really quickly. The range of a fission fragment is quite low. You can stop even the most energetic fission fragments with the wall of a soda can. Okay, so they render up all that energy in a very short distance once they encounter solid matter. But my focus right now, if you're going to understand reactors and weapons, is on the neutrons. This is this rough number, about 2.5 total. Actually figuring out what the average number of neutrons are coming out of fission and what their energy is another one of these great and ongoing problems. This is changing in real time, okay? Even for commonly used isotopes like the fission of U-235 and plutonium-239, we're right now working on this. It's called a prompt fission neutron spectrum, and it's an area of current research, okay? But that 2.5 number, that's not a bad idea to look at it at first. It makes a huge difference if that's 2.4 or 2.6. Okay, so really you just got to measure this thing. Okay, so let's just round that to 2, because I'm going to do really simple math. It'll be easier to go through this way. So let's say we have 2 neutrons produced in every fission. So what if a fission event occurs near another uranium nucleus? Okay, I've got my fission, one fission that goes on. Doesn't matter what started this. In this case, I draw the picture of a neutron coming in and hitting the uranium. But there are actually these other similar minor isotopes of uranium, plutonium, and the surrounding elements like americium, californium, et cetera, that have just a spontaneous fission rate that's going on. Just that one, it comes in, it'll hit that nucleus, start a fission, create 2, right? That's the second generation. And we're going to use this term over and over again. And then a third generation, which has 4 fissions in it, and on and on. So this series increases by a factor of 2 every time, subject to one great condition. It assumes that there's always a uranium nucleus nearby. That neutron doesn't just escape, okay? But we've already learned, right, that matter is not very dense. It's easy for neutrons to escape. You need big, thick chunks of matter in order for them to hit anything, okay? But if you have this going on, you can see, where would this stop? Would it? If you had infinite extent of uranium, this would just go on forever. 8, 16, 32, keep going. Okay, that would be a lot of uranium. Okay, but if you had it, this is what would happen. You would eventually, every neutron would end up finding another uranium. Now, of course, you eventually might have all the uranium on the Earth, or perhaps all the uranium ever needed in the cosmos. You know, if you gather it all into one place, wow, that was an accomplishment. Okay. But this is what would happen. It would just keep doubling at every generation step. Okay? Just jumping ahead, roughly speaking, in a weapon, we get up somewhere between 40 and 80 generations. Okay? Because we don't have an infinite amount, and it's not infinite in extent, and the conditions only go on for a certain amount of time. Okay. So how fast are these neutrons moving? Now, remember I said that the energy is about 2 MeV. That's the kinetic energy of each one of those. Okay? That's so small compared to their mass, for those of you who are technically aware of this, that you don't have to worry about relativistic correction. So the energy is just 1/2 times the mass times the velocity squared. You can solve for the velocity, and I want you just to note, or perhaps for a future homework usage, the cute little things that you can do here. If you put the energy in an MeV and you put the mass into the neutron in MeV per c squared, a neat little thing happens. The MeVs go away. You've got a c squared inside of the square root, so that becomes just c. The math gets really easy. It comes out to being about 6.5% of c. C is the speed of light, which is 3 times 10 to the 10 centimeters per second. Okay? So 6.5% is 2.5 times 10 to the 9 centimeters per second. This is quite fast. That's the energy of that neutron, and it will traverse distances really quickly. So if you want to build a reactor, or a supercritical reactor, we'll define that shortly, which is a weapon, you need to keep this velocity in mind, because it sets the time scale for the generations. At the end of the day, this stuff is these neutrons, as they move out, okay, are covering vast distances in really short periods of time. And so you have to make sure that there are enough targets there for them to be able to encounter. Now, if you remember, when we discussed reaction, the reaction rate is proportional to 3 things. This is the simple one-line picture. Okay? I've got a number of beam particles per second. This would be the neutrons per second that are coming in. I've got the cross-section. That's the size of the individual nucleus. And remember also times the probability that it does something. Okay? If it does anything, that's the total reaction cross-section. If it's fission, then I would call that like sigma sub fission. Okay? Times this thing, which is the product of the density of the target times the thickness. This is the areal density. Okay? This was, remember this? This is what we talked about in reaction. Right? So what I could do, I don't like this I beam thing. It's not like I'm going to tell you I'm drawing 10,000 neutrons per second. Let's make it just per neutron, per one neutron. Then I can talk about P being the probability. There you go. P being the probability for a reaction occurring per nucleus per neutron. Okay? So then I just have turned I beam into 1. This is just a probability. And what I have here is this product. It's the cross-section, which has units of area, centimeters squared, meters squared, feet squared, times target areal density, which is the number of atoms per centimeter squared. So centimeters squared times per centimeter squared, the units cancel. It's just a probability. It's a number. It's like rolling a 6-sided dice. You've got a 16.6667% chance of rolling. Okay, it's a probability. That's all this is. Okay. So I'm going to use these reaction plots over and over again because I think this is the way that you get comfortable looking at them. This is a plot for uranium-235 of 5 select cross-sections that I thought were interesting in this energy region. The top is the total. Right underneath that is elastic, and then, well, actually, right underneath it, this curve right here, for this nucleus, which is uranium-235, is fission. Okay. Then I have elastic scattering, and inelastic scattering, and N-gamma, which is neutron capture. I want you to look at the axes. This can be tricky until you get used to it. This is a log plot. So every tick mark means an increase by a factor of 10. So over here, this big tick mark is 10 to the minus 10 MeV. This one is 10 to the minus 5 MeV. So that means that the tick marks in between are minus 9, minus 8, minus 7, minus 6, etc. 1 MeV is up here, and this next tick mark over here is not 2. What would it be? I'm going up from 1. 10. That's right. The other axis is the cross-section in units of barns. Remember, a barn is a big number. 1 barn is right here. This 2 tick marks up, I'm at 10 to the 2 barns, which is 100. So what would this one be? 10. That's all. There you go. So if we look, if you look at the temperature, at that energy that we came in with, about 2 MeV, you're going to be slightly above, you should be slightly above the 1 mark. I didn't quite move this thing in the correct position. I put it on top. Okay. You see that the value that we have out here is around a bar. Okay? The line intersects this curve at about 1 bar. Let's go back again. This is it. About 1 bar. Okay? Now you remember what we had was that the probability of a reaction happening was the areal density of the target times the cross-section. So we've now looked it up and we've seen about 1. Okay? So that's about 1 bar. A bar is 10 to the minus 24 centimeters squared. Okay? So what if I want to know, what if I want this to be 100%? In other words, what if I want to figure out the areal density that gives me a 100% chance of interacting with a neutron interacting through this reaction? Okay? Well, to do that, all I need to do is replace the left-hand side with 100%. Now, this isn't really mathematically rigorous. You never get a 100% probability. What I could do is I can say that there is some average probability for unit length, but we're not going to get into that detail for the moment. Let's just give you a little bit of latitude here if you're technical. This is going to be approximately right. It's about 100% chance. Okay? Well, it doesn't like me getting close. Let's see. I need to use the clicker maybe. Okay. So I go ahead, and since I have 100%, it's just 1 on the left-hand side. I can flip this around, divide both sides by 10 to the minus 24. That becomes 10 to the 24 on the left, equals the areal density of the target. Okay. So if I go there, I can go through and now calculate another quantity. Remember over here, I've got rho times r of the target. Okay, that's density times thickness. This is kind of the thickness of the chunk. So I can now go ahead and turn this into a fission rate, okay, by dividing through by the density of uranium, which is 19.6 grams per centimeter squared. Okay, the rest of these numbers that I have here are just things that you need to take care of units. In the end, since I have cross-section unit that was 10 to the minus 24 centimeters squared. I'm talking about the cross-section for individual nucleus. I've got to tell you the number of atoms per centimeter squared, not the grams. That's what I'm all doing on the bottom here with these terms. All the math is spelled out here. And it turns out that in this case, for a one-line cross-section on uranium, which is the value at about 2 MeV, this works out to being just shy of 20 centimeters. Okay, there's 2.54 centimeters in an inch. This is about 8 inches. Okay, I used to have a leatherman. I carry it around with me all the time. I've lost it. If I unfolded that leatherman, it'd be about this long. That's roughly speaking the 100% of probability interaction distance for something with a 1 bar cross section. Okay, you need that thick a chunk. It's a macroscopic amount. Okay, but this was just looking specifically at fission. Fission has that 1 bar cross section. But remember that fission is just one of several possible things that can happen when a 2 MeV neutron comes in and hits the nucleus. If I were to put all of it together, the distance would be much shorter. And that's because this number would change. Remember this, which is 10 to the 24 per centimeter squared, was the reciprocal of the cross-section. It was 1 over. So if I made that number 10, this number would have been 10 bars. That number would be 10 to 23, not 10 to 24. And roughly speaking, that's about right. It turns out that your reaction rate, if you just define a reaction as hitting, I don't care what happens next, and you ask what's the distance then, it is about 1/10 of the value, okay? Or about 2 centimeters, roughly speaking. 2 centimeters, less than an inch. And here you have the fundamental problem with reactors and with weapons. You need a big thickness in order to cause fission to occur, to get the energy out. But even a small thickness, less than an inch, is enough to give you a scatter. And what is that scatter most likely going to do? We'll go into that. Not fission. Only 10% of the time is it going to be fission. At least up at the energy where the neutron is born in fission, which is 2 MeV. That's the fundamental problem. Or as I say in my yellow takeaway box, if you have a chunk of 235 uranium that's a lot thicker than 2 to 10 or 2 to 20 centimeters, there are likely to be many reactions which could lead to more fissions. Okay? But I need to get it that thick. If not, all that will happen is that neutron that comes in, instead of inducing other fissions, will bounce around like a billiard ball, hitting the bumpers on a pool table, and then doing nothing. Okay? So, therefore, this already tells you that I need to make a reactor a lot bigger than these distances. And we do. Reactors, generally speaking, are bigger than 2 to 20 centimeters in size. Okay. It's kind of tricky. There are things you can do to make them smaller, but you know, your tricks begin to really run out. The truth is we need to just get a lot of material stacked around so that the neutron born at least toward the middle has a chance of doing a reaction. All the ones born outside, I have a really good chance of just leaving. Those right on the very outside edge, half the time they scatter, they just leave. Okay? So you're constantly leaking out. So this picture of every generation doubling is not reality. Remember, these things are moving at 6% of the speed of light. So really quickly, they're out. Okay? Okay. Something with static electricity. This is interesting. I'm going to try to keep doing it. If it does it again, I'm going to take a moment and try to switch in this guy and see if that works. Okay. So let's say we have a reactor that looks roughly like this cylinder. This is a neat shape that I can bring up in PowerPoint. Okay. I introduce in a neutron somehow from the outside world. And by the way, we're being hit by neutrons all the time. They're coming from cosmic ray showers, from radiation from space coming in here all the time. And I just went back and forth this week to Washington, and I got my dose of neutrons, like putting most of the atmosphere behind me. Okay. So neutron comes in and it causes a fission event. And I produce a couple of neutrons that come out, and they produce a couple of fissions and a couple more neutrons, and so on and so on. They scatter through this ball, okay? Sometimes the neutrons stay inside and cause other fissions. But sometimes they don't. The neutrons leave. Obviously, as I make this thing bigger and bigger, that ratio becomes more favorable towards fission occurring, right? It would also depend on the shape. If I have a shape that has a very high surface area to volume ratio, then I'm going to have a much greater probability of leaving. Because remember, once you leave the spot, you're gone. This is a reactor sitting all alone in space. Space reactor, okay? There's nothing around it, okay? So this ratio of the number of neutrons that are born that stay in and induce more fissions versus the number that go out, this ratio is called K effective. Okay? And it's something that we use largely to describe reactors, but we don't have to. We could use it as well to describe weapons. We just don't, because the number tends to be a lot bigger than 1. When K effective is 1, I'm balanced. The rate of neutron production from fission events, or from other events, any event, is balanced out by the leakage rate coming out. That's where you want to put a reactor. You want it can't be too low, because then it will turn off. And it can't be too high, because, well, that's a bomb. Okay. Actually, what it really would be if you make it go high, almost immediately, the thing expands slightly, the density goes down, the reactor turns off naturally. There was, by the way, a natural nuclear reactor that was formed, when was it? It was before dinosaurs. So this thing was around 1 billion years ago. It was well before dinosaurs, near Oak Grove, in what's today Africa, but back then it got stripped apart several times. There was a natural reactor that occurred. That was back when uranium had more 235 in it than it does now. Okay? And it did exactly that. It pulsed. It got hot, it went above critical, it expanded, and it cooled immediately, because the minute it expanded, the reaction rate dropped. So the fission's natural. So what is the average time rate between these collisions? Well, it would just be, again, collision. I'm not talking about fission, just anything happening. Okay? Well, the distance for anything to happen is about 2 centimeters. That was the velocity that we had before. So the time between each head works out to being about 10 to the minus 9 seconds, or something we call a nanosecond. But remember that fission was only 1 out of 10 of those events. So I can then say, what's the average amount of time between fissions? It will just be 10 times longer. And that's about 10 nanoseconds. And so this is a very natural unit to look for any assembly of fissionable material in the presence of neutrons, probably of its own generation. We call that unit a shape, right? So that's one shape is 10 nanoseconds. And that's about the time that it would take for that neutron, born in its birth energy, to move out and cause another fission. Now, this is only approximate. The truth is that that neutron comes out, and one of the things it can do is it can bounce off of a neighboring uranium nucleus and not cause fission, but it can lose a lot of its energy through a process called inelastic scattering. It excites a state up in U-238. Okay? Like in a reactor, most uranium is U-238. I'd like to point out at this point, because I can't help myself, that we've never actually measured that probability as a function of the energy of the incoming neutron and the angle that it goes out at. We've never measured that probability as a function of both of those two things. We built reactors until they worked, and then we stopped. So even now, we don't have really a good number for that. But we have an idea, because we can model things and we know that certain assemblies work. So a lot of what you're going to see, I'm presenting this up at this point as being like just solid math. But often, you know, those cross-section curves that I have, someone has to get that from somewhere. We either have to measure it or we try to calculate it. And as I was just saying today here, nuclear physics is a field of science where we don't have a great predictive capability. We have a fantastic descriptive capability. All right. Any questions? Are people following me? That was? Yes.
Sorry, the 10 nanosecond one shape is the 10 nanosecond per
would be, yes, the time scale between collisions that would cause fission. Okay. Again, the vast majority of them, you're still having a collision rate of under nanosecond, but it's just not doing fission.
Where do you get the story with the 2 centimeters or 2 to the 10?
Very good. The 2 centimeters was from back here. Okay. The 2 centimeters was from the fact that this cross section, for doing anything, it's the total cross section curve. The top curve is total. Let's do anything. That curve is at 10 barns. And if I go and take that 10 bar number and put it into this equation that I had up here for the rate, for this rate, okay, if I put 10 barns in, it actually comes to the previous slide, okay, right here I had 1 barn, because here the fission cross-section was 1 barn, okay, but if I go to 10 barns, then this number here, which I put in, this 10 to the minus 24, that would become 10 to the minus 23. And so when I divided 100% by 10 to the minus 23, I would have 10 to the 23 over here, instead of 10 to the 24. And when I came over here to this line, this is just a continuation. This is 10 to the 23. The rest of this is the density of uranium. This is something called Avogadro's number. It's the number of atoms per 235 grams of U-238, okay? And if I work this math out, this is just the density, okay? I have the cross-section divided by the density is the R. That's just from back here. This is cross-section, right? Cross-section times density times R, okay? So this is just the algebra of, hold on. This is the algebra.
Okay, so I get where the 2 comes from.
The 2 comes from the fact, when I calculated that before, it was about 20.
20, so then,
But now that it's 10, it goes to being 2.
okay, I understand that part. Now where does the 2 times?
Remember that this is the distance between collisions. 2 centimeters is the distance between collisions. Okay? So if I take the distance and divide by the velocity, I will get the time. This is like velocity is distance divided by time, okay? So what I've done here is taken distance and divided it by velocity. The equation is that the velocity, right, equals distance over time, the number of miles per hour. So we calculated that before as being about 2 times 10 to the 9. Okay, 6.5% of the speed of light. Okay. Is that good? Thank you for slowing me down and asking these questions. That's great. That's audience participation points. That's exactly what I want to see. Okay. All right. So the chance of a collision leading to fission is really small, right? You've already figured this out. Only 1 in 10 collisions at the birth energy of the neutron is going to lead to fission. The most likely thing is just that it bounces off and does nothing else. Or it bounces off and leaves some energy behind. So it's kinetic energy. You can think of it as like what would happen if I bounced you off of a trampoline. You don't actually go up the same initial height, right? You leave that noise. They trampoline forms. Okay? So if I look here at this birth energy, I can look along these curves. I'll see that the fission cross-section is about a barn, but the elastic scattering cross-section is about 3 barns. That's just elastic alone. So 3 to 1 for that. But what happens if I can slow that neutron down? Remember that this is the incident energy of the neutron. The birth energy is about 2 MeV. What if I can slow it all the way down to room temperature? Okay, that 25 millieV. You know, I get, look how many decades I get to march back. Remember that 86 kilovolts is 1 billion degrees? 2 MeV is really, really hot. It's actually the temperature on the inside of the grids. Okay, when it's evaporating neutrons, it's about that temperature. It's a 10 or 20 billion degrees. Okay, so if I am able to slow it all the way down, now everything is different. The fission cross-section is close to 600 barons, and the elastic cross-section is 100 barons. I've actually turned things upside down. At high energy, fission is an unlikely thing to occur in every collision. And at low energy, it's the likely thing to happen. So this is the key to reactors and to weapons. You want to slow the neutrons down so that you can move to a different part of this log plot. You see how all these curves are going way up on the y-axis? That's what you want to do. This is particularly the case for uranium-235 and plutonium-239. Okay? Now, there's one other thing to note here. If I'm in a reactor, most of the material is still not U-235. Okay? Most is U-238. Where the fission cross-section, if you look at what happens here now, I'm starting here. Here the fission is about a half a barn. Elastic is about 3 barns. I'm just picking on elastic because it's the biggest single other thing that goes on usually. If I go all the way down here, though, the fission cross-section, I'm really sorry to anybody who has any issues with eyesight. There is a light blue color here. Can you see that? Like a aquamarine color? That is the fission cross-section. You notice it basically disappears. It drops off the scale of this chart. Fission does not occur at these low energies for U-238. Other things still go on. You've got capture. The red curve is capture of a neutron, which would turn to U-238 to U-239. You've got elastic scattering, and you've got, and that's pretty much it. It's those two things that make up the total cross-section. Okay? So just keep this in mind. If you're in a reactor, you have 7% U-235, this 93% stuff is not doing any good for you. At least not to get things going. We'll talk about that a little later. It helps a little bit later, but mostly it's just a spectator. Or actually, it's a source for plutonium. That's another use for it. Okay? So if I want to make a reactor go, I need to optimize 3 things. One is I can increase the U-235 to U-238 ratio. That's the obvious thing. Because U-238 will not, when you slow the neutrons down, it doesn't do you any good. It doesn't create more fission probability. But U-235, it does. So if I move to ever higher enrichments of U-235, I'm going to increase the fission rate. I'm going to increase the probability that every one of those nuclear scatters leads to a fission. Okay? And again, you can see that just by comparing these curves. Pointing out here again. Okay? You've got the fission curve up here where my cursor is. This is U-235. It's almost the entire total process. Here's U-238. I can't put my pointer down at where this light blue is. It's totally off scale. It's about a microbar. Okay? So trick number 1 is to obviously increase the U-235 concentration. This is really costly to do it. We'll cover that later this semester. It's just hard. You can do it, but you pay a huge energy price to do it. And you go through a heck of a lot of uranium to get a little bit of usable U-235. Okay? Way number 2 is to slow down the neutrons. And that's what we tend to do in reactors. Most of our plan is to slow the neutrons down by some mechanism to increase the probability that when they actually hit, because they miss most of the time, that they'll make a fission occur. How does this sound, people? Are you following this up to this point? I want to make sure.
So, a quick question.
Yes.
So I was wondering, is it practical to put like reflectors around the
Reflectors. Absolutely, it's practical to put reflectors. But it turns out that you need a lot of it. Okay? You do. You can put a nucleus around your reactor, a material with a nucleus that has a very big elastic scattering cross-section. In that case, the neutron might turn around and go back in the correct direction. That can happen. People of a certain age, you might remember the cartoon Ricochet Rabbit. Ricochet Rabbit. It can bounce back. It can happen. But you really need a lot of material to do that. Absolutely. Reflection is one way to do it. There's a device at Los Alamos, which has one of the coolest names in the world, I think, ever for any sort of science device. There's actually another one as well at RTI in state New York. It's called the lead slowing down spectrometer. Listen to that. Lead slowing down spectrometer. It's basically 1 meter by 1 meter by 1 meter cube of this incredibly toxic, dangerous thing that nobody ever wants in their lab, but other people hold back. Okay? In a big cube, when you bring neutrons into the center there, what they do is they reflect around, they bounce off of things over and over and over again. They undergo on the order of 300 bounces. And because lead is very heavy, they don't lose very much energy. But I'm jumping ahead of myself. And so you can keep them around for a long time. Okay? And they eventually slow down against the day. Okay, I'm sorry for that, by the way. When people ask a good question like that, I'm going to go off a little technical bit so that the people who like the technical stuff can hear on the little side of this. The last thing, right? So I can increase the uranium-235 fraction, I can slow the neutrons down and take advantage of bigger cross sections, or I can make the assemblies rho r larger. Now, up to this point, we've been saying, why do you keep putting density and thickness together? Remember that has the units of this thing is atoms per centimeter squared. It's inverse cross section. But the other reason why I do it is that you're used to thinking of these two things as being constants that are a property of the material. Materials have certain densities, right? Well, in a weapon, that's not the case. We actually drive the density up, and I'll get to that. But for the moment, I'm going to keep them together. If I make the rho r larger, this will work. Okay? All right, so let's do the first point. The enrichment of U-235, and in this case, this is a plot that shows U-235 and U-233. So it's enrichment fraction versus fraction of U-238. What this represents is the critical kind of mass limit as you were to increase the enrichment of the nucleus that actually can fission relative to the one that can't, which is U-238. This is taken from Forsberg's definition of weapons usable uranium from Oak Ridge. Okay, and what you see is that as the percentage of U-238 goes up, the amount of material that I need, total uranium that I need, to create something which can actually go critical, where there's actually a chance of the neutrons causing enough fission so that the leakage rate balances out the production rate. Look what happens with these curves. They diverge. They go up to, well, to infinity. Okay, they become ridiculously large. It's 1.6 metric tons at the top. Okay, and so really, you pay a very steep price for that. Now, that being said, you can pay that price. You can build something that works even at natural concentrations, or even potentially below natural concentrations. But there is a lower bound to what you can do. So this is one approach, and that really says it all. It should be clear, if one nucleus fissions and the other one doesn't, then obviously putting more of the nucleus in the fissions drives up your chance of achieving criticality, of getting K effective to being 1. Okay. Now, how do we slow down the neutrons? Remember, that's approach number 2. Okay. Well, the answer is to collide the neutron with a proton from water. That's really the primary trick that we do. Okay. So if you have one single neutron coming in and hitting a nucleus, okay, a heavy nucleus like uranium-238, it bounces off with basically the same energy that it had initially. This would be what would happen if I took a fly and bounced it off of an NFL football player. Bounce right off, believe me, that football player is not going to recoil very much. It is an imperceptible small amount, but mostly it's not going to do it. This is no more complicated than understanding that uranium-238 is about 238 times more massive than a neutron. Okay? Now, if instead I were to bounce it off of water, a straight light with this up there. I bounce it off, in particular, the proton that's in water. Remember that water is H2O. There are two hydrogens in there. If I bounce it off the H2O, then on average, you end up with a back-to-back scatter that averages over the whole range of about 1/2. The energy is half. Every collision halves the energy. Okay. Now, there is one big thing that I'm missing here. If this V initial is high enough, it can leave energy behind in the uranium nucleus itself, not in the recoil of the nucleus, but inside of it. You can excite the uranium up to an excited state, and all that energy is gone. That's like bouncing off the trampoline. Every time you bounce off the trampoline, you leave energy behind in the trampoline. Okay? And it heats it up. But that only works once you have enough energy to excite at least one of the states in uranium. The first one is at 44 keV, which is quite high compared to room temperature. So collisions with protons are a great way to slow down neutrons, and we call that moderating them. Okay? So we can now, through multiple collisions, where you lose a half every time, you can say it's on average, you will scatter down from your birth energy of 2 MeV down to about 25 millieV. And then you won't really get any lower. And that's interesting, because that's sort of the temperature of everything. It's the velocity of everything that's going around. So if you bounce off of something else that is the same velocity as you, the two things, there's no longer a resharing of energy. It's just you change directions and go on your merry way. Okay? It becomes more like a mosh pit than a slowing down process. Okay? So these are the main mechanisms that you have in a reactor. You either slow things down by multiple collisions, or you increase the uranium enrichment, or a bit of both, which is what we generally do. We bring the uranium up from its 0.7% number to some sort of a suitable number, depends on the reactor design, but it's several percent. And it's through these collisions, okay, these collision properties. There is a price to be paid in these collisions. Every time you collide as a neutron off of hydrogen, there's a possibility that you will not collide, but that you will stick. That the neutron will get absorbed by the proton and form a deuteron. Now that's not a problem, except that the neutron is gone. Now that neutron is not available. So if you think of it this way, it has to survive the collision process long enough without getting captured. So you have losses to that. There's always a loss of the neutrons going into that capture process. And the water in a reactor, slowly over the course of time, the hydrogen converts itself into deuterium. Okay? Sometimes we call that hydrogen 1, we call it protium, because it's for a single proton. So hydrogen 2 is deuterium. Hydrogen 3 is tritium. So the next few slides, I'm going to put in a bit more of a math example. I'm going to go through them slowly, but this is going to be like what you just saw before when I was doing, where we figured out that 2 centimeters and 20 centimeter things. These are all math steps. I'm happy to go as slow as you want through this, no problem. But I believe I've written out every step. I haven't pulled one of those marvelous fast ones that people do where they just omit a math step. I think it's all in here. Okay? So we're going to look, first of all, at a reactor that's based on natural uranium with 99.28% U-238, 0.72% U-235. Okay? Now, we've assembled this reactor in some shape with some density, and there's a certain fission neutron generation rate and a certain neutron loss rate. And remember that ratio between them is this K effective. If you have K effective being less than 1, the system is subcritical. What does that mean? It means that if I put a neutron in at the beginning, eventually everything stops. I can put any number of neutrons in at the beginning, but everything's going to stop. Eventually, everything's going to leak out. That doesn't mean that you won't have fissions going on, but you won't create the fissions fast enough to replenish the neutrons you're losing by exit. Then you have K equals 1. The system is critical. And that's where you want to be for a reactor. You're losing neutrons at the same rate at which you're producing them. Or you have the system at K greater than 1. In this case, the system is supercritical. It's just language. Sub and super, and of course critical in the middle. Okay? Now, the reality is that when you start a reactor up, it is sort of momentarily supercritical. It has to be. There's a lot of neutrons that are running a reactor, and it starts off with nothing. Okay, so you start it off, and it is temporarily supercritical, and then it reaches an equilibrium rate, where loss rates are balanced out by generation rates of neutrons. Steady state operation requires that K be 1.00000 all the way up to a very long distance. Okay, that's what we have to do. It's really rather remarkable that we could make any of this work, given the fact that we didn't, all those curves I've been showing you, they're our best guesses. We often, and all of their uncertainties are correlated to one another. So the fact that we're able to make this work is testament to the fact that we actually built a lot of things that didn't work as planned, until eventually something worked as planned. Okay, and we still have this problem that when we try to build something new, because we don't really know the numbers, sometimes it doesn't work. And we're never allowed to have it work better than predicted. That would be very bad from a public relations standpoint. So, U-235.72% abundance. I want you, here are, and by the way, I'm sorry, I'll do this periodically, depending on your definition of room temperature. Sometimes people like to go to 30 millieV, it's the nearest decade, and there's multiple of 10. That's 30 millieV, it's like 25 millieV, it's room temperature. Think of it as slightly warmer than room temperature, which in a reactor you have. The cross-section for fission is 584 barns. Remember I said it was about 600 down there? The cross-section for everything else is about 97 barns. So in other words, about a 6-to-1 ratio. Every collision will cause a fission. That's what it is if I moderated neutrons. If I look at U-238, which is the balance, 99.28%, there's basically no fission. That's a 10 to the minus 6 barns. But there is a bunch of other going on. Okay? So I can define a quantity, which is PF. It is the probability that from a given scatter, I will have a fission event going on. If you want to think about this, this is the second part we defined cross-section. Cross-section was how big the nucleus was. But the cross-section for a given channel was the fraction of the time that it went through that. That's all this is. This is a number, again, from 0 to 100%. It's the cross-section for fission over the total cross-section, which is the cross-section for fission plus everything else. Capture, elastic scattering, inelastic scattering, neutrons in, protons out, anything. Okay? This ratio, this is the probability for fission, EF. Okay? Now, I'm just going to flash something up for a minute. Don't be scared. I see you looking very concerned.
Well, no, I'm just confused because under the 238 abundance, that you have 235.
Oh, thank you. That's a typo.
Okay.
That's a typo. Fantastic. I put these things in to make sure that you're paying attention. Okay. That's a typo. That should be U-238. Let me just be clear here. This one right here.
Yes.
That's an 8. That's an 8 in a virtual world. Okay. Thank you for being confused. Okay. Okay, so this last part, if you're scared by differential equations, close your eyes. But if you like differential equations, get ready for a treat. Okay. This is what's going on. This is the number of neutrons per unit time. The NDT is equal to Kn minus n over tau, where tau is a particular characteristic time. This is how we define K effective, or why K effective is 1. This is just a balancing act between production and loss. Okay? Go ahead, you can open your eyes again. Okay. All right. So we're continuing with this. Let's see if I wonder if I continue to make that same typo. Maybe I didn't have an opportunity to do it elsewhere. Yeah, see, I nicely went and put in the numbers here and saved myself. So this thing where I put a bar over the top, okay, what that bar represents is an average. And we use that in math all So if I look at what the average fission cross-section is for uranium that's natural, in other words, again, 0.7% U-235, 99.3% U-238. It works out to being 4.2 bars. This is just an average, right? I got 584 and 0. And when I average those two, but take into account the fact that U-235 is really rare, it works out to being about 4 bars. The other category ends up being about 3.43 bars. Okay? So what this means, in essence, if I don't no longer look at a single nucleus, whether it's U-235 or U-238, but I try to say what's the fission probability for hitting any uranium nucleus in the reactor, it's about 0.55. It would be the 4.2 bars over 4.2 plus 3.43. Okay? So that number looks pretty good. Okay? And again, it's because once I've slowed all those neutrons down, now they have a pretty decent chance when they interact with the U-235 of producing fission. Okay? 0.55. So if each fission produces an average of 2.5 neutrons, I'm just going to be a little bit more accurate here, right? We could just do this in numbers, okay? Then the number of fission neutrons produced per thermal neutron in is just the product of these two. It's about 1.38. Okay? Because remember that, up to this point, I've been looking at the fission probability. This is a fission probability per, this is the fission, this is the fission probability over here is 0.55 for 1 neutron. But I get 2.5 neutrons. So this is what it tells you. 1 neutron in, on average, 1.38 neutrons produced and available, ready for service. That's what this looks like. Now, if I enrich this to 3%, you would just go over here and jigger these numbers here. That's 0.72%, that's 99.28%. You can jigger these numbers, turn them around, and you would end up with 3%, that number going up to 1.84. Okay, you can play your own games later and see what happens. As I boost the fraction of U-235, I'm bringing that number up. Okay? So we can now, and we keep, oh, by the way, this is the Greek letter AF. So we can combine these two factors with 2 more pieces of information to get something called the 4-factor formula. Okay? So the 2 other factors that I need to include are the fact that fast fission neutrons, the ones that are still fast, right after they're born, before they've collided many times with hydrogen and slowed down, can produce more neutrons via things like end-to-end reactions. They can break things up and create more neutrons. Not a lot, but it's a little bit. In addition to fissioning, reactions, etc. In addition to inducing fission, and this leads to another number slightly bigger than 1, which is this epsilon sub fast. Okay? It reflects the fact that on their, you can think of it this way, these fast neutrons on their way down actually create a few extra neutrons. It's not very important, it's about 3%. There you have it. So these neutrons, of course, need to slow down or moderate through collisions on light atoms. We usually, in our reactors, we use hydrogen and water. The Canadians use deuterated water, which has less loss to capture. Old reactors and reactor Chernobyl used graphite. Carbon can be used as well. It's not as effective, but it's got some nice thermal properties. You don't have to worry about it melting. You don't have to worry about it burning, but it won't turn into steam and disappear. Requires in the order of 100 collisions. And every time you have one of those collisions, remember, you could lose the neutron. The neutron not just get knocked out of the system, but it can get absorbed and be gone. Okay? And that leads to another factor called F, or the thermal utilization factor. It's a number less than 1. It represents the fact that you do lose some of the neutrons. Okay? You put it together, and you have something that gives you kind of this ultimate simple case, K infinity. Why K infinity? Notice that nowhere here have I talked about the size of this thing. I haven't talked about how big it is. Yes? There's no leakage. Okay? There are other things that can go on, but there's no leakage. Neutrons can disappear by other mechanisms. There's a better formula, which we'll show in a moment, which just includes 2 more factors to show that. Okay? And that's a 6-factor formula. That's what this looks like here. Oh, in fact, it's my next slide. Huh? About that. The 6-factor formula. I'm going to put this up here. I think it's important to see it once. A couple of the factors here are going to look completely unfamiliar with you, but unfamiliar. Here we go. It's a couple of these things. Actually, this should be down below. The P box should be around P resonant capture. You see this thing I call the resonance region? We've been glancing by that, but it's where the cross-section curves go jagging up and down. There's actually, at every one of those jagged peaks, there's an enhanced probability of capturing a neutron, having it be pulled out of the system. The important things to note here are these 2 terms in red, LF and LT. They're the probability that a fast neutron does not escape the assembly, so now I've got escape coming in. And that's, this should be LT, and the probability that a slow neutron should be LT. A slow neutron does not escape the assembly, okay? So that's dependent on geometry, those last 2 factors. Before this, I haven't really concerned myself with it, okay? So there's another way that you can look at a reactor. We primarily look at it as a way of producing energy, okay? But I think of a reactor as a way of freeing up neutrons. And what do we then do with those neutrons? Remember, once I liberate a neutron, I've got uranium-238, okay? And I've got 146 neutrons in there. Once I start liberating some of those neutrons, what do they do? What does a lone neutron do in space? What does it do? It decays. It decays. It does not hang out forever. It only hangs out forever if it's bound up in a nucleus. Okay? So these neutrons, which have been built up over the course of aeons in big stars, and now we know neutron-star mergers, okay? They're there as a resource, and they're trapped in the uranium. We free them up, and we can start doing reactions with them. Once we free them up, and really we can only free them up easily in the case of U-235. And actually, that's the only thing that really does this. That little bit, 0.7% of all uranium we have, that's our source of neutrons. And you can't store it forever because it just goes away. Okay? So we can talk in nuclear engineering about kind of the neutron economy. Once you free these neutrons up, they start to do things. But it's a weird sort of economics picture. We have an economics major all the time, I think, right? Yes. Yeah, because the money goes away. Okay? Yeah, the money actually goes away. It eventually turns to nothing. Okay? So let's say we start with 1,000 thermal neutrons. So now I throw a bolus of 1,000 thermal neutrons into the reactor. What can happen? Okay? Well, it'll come in and it will induce fission on the U-235. And that produces more neutrons by virtue of that eta factor. How many more? We're up to 1,330 fast neutrons. So this is the beginning of supercriticality, right? I put 1,000 in, I get 1,330 out. Okay? But there are losses. The first loss that happens, okay? Well, wait, one more gain factor. These are boarded fast neutrons. Remember there was that 3% extra little piece that came along because they're fast? So the number actually goes up a bit, 1,370. Okay, so I made more fissions. Now the fast nature of the neutrons gives me a bit more of a boost. Okay, but now I go through and I lose some of these things, this LF factor. The fast neutrons leak out. So actually I lose 70 of them here, and they're down to 1,300 neutrons. Now I need to slow those neutrons back down again so that I can take advantage of that big cross-section in U-235 at low energies. Okay, so I put them through a moderator, but there are losses in that moderator, rather significant ones. I lose 130 of those neutrons to get the rest down to the thermal energies that I need. So now I'm at 1170. Okay? And then, of course, those neutrons can leak out, just like the fast ones could. And I go through, well, sorry, there's actually two things here. These can be captured. I got them in reverse order. The first step is that those slow neutrons can get captured, in which case they're gone, or they can leak out. Put those two together, and you kill off the remaining 1170 in 2 bumps, and you're back at 1,000. And that's a reactor. Your production rates and your loss rates balance out. And actually, we have a number of designs that do this quite robustly. They will just sit there and regularly go through balancing things out and creating not just energy, but a constant stream of neutrons. Remember, at the end of the day, I did create, right, I was all the way down here, I was up to 1,370 neutrons. Every cycle through, I'm losing 37% of my production, which means that reactors become also a very valuable source of neutrons. And we can use those neutrons for a number of different activities, both scientific, medical, okay, for research purposes in general. Okay. Now, I brought these curves up before. Let me just show something here about these. This is this loss through capture over here. So we have to use hydrogen to bounce neutrons off in order to slow it down. But every time there's a chance of capturing one of them. If instead, what is that chance? Well, thermal energies, it's 100 millibar in cross-section, okay, for capture. If instead of using just normal hydrogen, protein water, if I use heavy water, which has got deuterons for the hydrogen, chemically it's identical. Okay? That capture cross-section drops down to 0.1 millibars. So it drops down by a factor of 1,000. What does that mean in reality? It means if I want to make a reactor and I have less U-235 available, let's say I'm using natural uranium instead of enriched uranium, then one way to do this is to switch to heavy water. And that then has the advantage, it also more completely utilizes the neutrons that you have. Okay, it's a better economic picture. So a side effect of light water reactors is that they also produce plutonium. Okay, and this is how that happens. Here are the curves again. I'm just going to keep throwing these up until you get comfortable and reasonable with them. Okay, this dashed red line is room temperature, again about 25 to 30 milli eV. And you can see that this purple color, which is capture, oh, I just realized that I used the wrong curve here. This should be the curve for U-238. And I used U-239. I'll change this. There's a big capture cross-section even in that. We go back to that chart, U-238 curve. Here it is. This is U-238. Here's the Indiana cross-section in red. So if I go to room temperature here, I'm actually got 3 bars of capture. Okay? It's easy. You can go and grab any of these and look them up. See, this is the red here, which is the lowest curve, is the capture curve. And what it does is it turns U-238 into U-239. Now go to this curve and look at this equation up here. You capture that neutron, you make U-239. After 23.5 minutes, it decays into Neptunium-239, which after 2.35 days decays into plutonium-239. Okay? So, why is that important? Plutonium-239, like U-235, when you moderate neutrons, it can fission. If you slow the neutrons down, it can fission. Now, does anybody know how? So why don't we just start off by making bombs out of plutonium? In fact, it's better than making It's going to higher fission probability. Why didn't we just start by doing this? And the answer is that there wasn't any of it around. Okay, it's got a 24,000-year half-life. So there probably was plutonium-239 around in the cosmic debris that eventually coalesced to form the Earth, but all of it decayed away a long time ago. We had to make more of it, reactors. First of all, we had to discover it, which Glenn Seaborg did here, and then we had to make more of it. Okay. So, good. This is the end of reactors. You've learned everything that you need to know right now about reactors. Okay? And the next thing is to go on to weapons. Now, I can take a break here for a moment, and let me ask you guys if you have questions. It's where I thought we might be, but we might be able to get out to this point and we'd be ready to start talking about weapons. Questions? Mull over it. We can go back and have in that open-ended Q&A, we can talk about this a bit more. So reactors use fuel enriched in U-235 to produce energy in a sustained and what I call a static fashion. The whole idea is that neutron economy is balanced out. You're just continually producing energy, you're producing neutrons, you're shooting them into the environment around you, activating your steel and creating all sorts of sad side effects, or maybe using them for other reasons, but you're generating energy all the time. Okay? In contrast, a fission weapon generates energy in a runaway fashion by maintaining supercriticality for a prolonged period of time. And again, how long is prolonged? Sort of 80 generations, and those are about a shake, a quarter of a shake each. Okay, so this is not a very long period of time. You're talking about microseconds of assembly time. But that exponentiation process, that times 2, times 2, times 2, or actually it's times 2.5 to the end, right? 2.5 for the number of generations. You don't need to go for very long to get a tremendous number of neutrons produced. Now, thermonuclear reactions, that's another part of weapons, and it really is a separate component. It can be used for two purposes. One is to produce additional yield. The thermonuclear reaction, the one that we most typically use, is this one, which is tritium and deuterium fusing and forming a neutron and an alpha particle, yields 17.6 MeV of energy. A lot less than 200, but it does it with just 5 mass units. So you need a lot less mass of deuterium and tritium. But tritium is unstable. Okay, so you need to be creating a continual supply of tritium if you want to keep this going on. There are other ways that you can do this. You can break up lithium-6 into tritium through another thermonuclear reaction and then react that tritium. Okay. So one way is to produce additional yields. And the largest weapons produced a significant chunk of their yield. Not most of it, but through this mechanism, through thermonuclear reactions. But the other great value of thermonuclear reactions to weapons design is that they produce neutrons. This neutron right here is really important. Because if you create a whole chunk of neutrons in the middle of your leaky assembly, you push the neutron economy towards positive again. Okay? And that is something that we call boosting. And I'll talk about that as well. Okay? So do you remember me? I drew this picture a couple of days ago just to kind of show you. This is the kind of typical picture of a nuclear weapon. And going forward, I'll talk about the physics in great detail about things and how everything happens in steps and orders in modern nuclear weapons. Okay? But we're not going to talk about shapes and details very much. Okay? There's a primary and there's a secondary. The primary is the part that draws, it's the first step in this device, and it involves the vast majority of its energy through fission. Fission is induced by neutrons and slow neutrons in particular. So it wants the temperature cold. In contrast, the thermonuclear component of the weapon, the secondary, wants it hot. Okay? So the first weapons produced virtually all of their energy from that primary component, from fission. Okay? So to make a runaway fission reaction, we need to optimize the terms in that rate equation. Right? This was that rate equation. Areal density, again, the number of neutrons I'm throwing at each nucleus per second, and the reaction rate. Okay? Now that reaction I'm interested in here is fission. So I can't do anything about the cross-section for fission. I have a trick to make the cross-section for fission go up. I can slow the neutron down, but it will always have roughly the same value. And believe me, people have tried. There's been interesting attempts to try and change the nuclear properties in some ways so that you can enhance the fission cross-section. That's largely the stuff of myth and legend. Okay, this is just fixed. It's what we came into the universe with. Okay? Remember that this second term is just the number of neutrons per second that we have, so it's not really relevant to this. I want to increase the rate. I can't do anything about the cross-section, and I want to increase the rate per atom, or per nucleus, per neutron. Really, the only thing that I have left is this part, the areal density of the material that I've got. How dense is it and how thick is it? Rho and R. This we can change. We can assemble a dense, which means a high rho, large, or thick, meaning a large R, mass of uranium-235 or plutonium-239. Basically, all of the early weapons development was focused on this, trying to get the correct assembly put together. So, first of all, I want to assemble something into a shape. What shape has the highest density per unit, let's say the highest volume per unit surface area, the highest density per shape? What shape does that? A sphere, obviously. That's what happens. Gravity over the course of time will go into roughly a sphere. That's it. Sphere. In our 3D world, that's what it is. So I start off with some initial ball of, let's say, uranium or plutonium, the given initial radius. And basically what I need to do is compress this thing, okay? If I compress this thing down by a factor of 4, okay, which is an option in PowerPoint, you can choose, 25%, okay? If I do that, and if I don't lose any mass in the process, what happens to the density? Let me just ask you notionally first. What happens if I have a ball of metal and I crush it down to 1/4 of the radius? What's going to happen to the density? It's going to go up. That's obvious. And I think I mentioned this before. The people who used to be in the primary division at Livermore, B division, called themselves metal pushers. Because this is what they did. They pushed metal. They studied going, this is really a natural also. Plutonium is a really dense, consistently chemically reactive, poisonous metal. Okay, uranium is not a good thing to have for much either. Compressing this is a pretty unnatural act. When was the last time you shrank a ball of steel by a factor of 4? Okay. It doesn't happen easily. You need a lot to do that. Okay. Well, remember that density is mass per unit volume. This is the volume of a sphere, 4/3 pi r cubed. So I put it in, and what do you see? If I made r into r over 4, the density went up by a factor of 64. You say, now wait a minute, the r, the radius, that went down, right? It went down, though, only by a factor of 4. And now you see why I've always been lumping rho and r together, okay? Because look at what happened to the areal density. It went up by a factor of 16 times. All of these very loosely associated nuclei that are very far apart got crushed together, such that the area they covered is 16 times higher. That's really the way you make a supercritical assembly. You bring everything together like that, okay? Remember, that's because of that factor, the rate goes up by 16-fold, okay? I just have one more slide. I can finish this. Okay. We have a few more tricks up our sleeves. And I'm going to stop at this point. I'm not going to go into boosting. That'll be the next lecture. And it's exactly what Bill was asking me about. We can add a reflector on the outside. that has the correct nuclear properties. What does correct mean? That reflector should have which kind of a cross-section, big or small? What should be the likelihood of that reflector to capture neutrons, big or small? Small. Small. How about elastic scattering? Big. It should bounce things back in again. That's what it should do. Turns out there's a couple of good materials for doing this, beryllium being noteworthy as one of them, but there are others as well that can be used for this purpose. And this has to be pretty thin to have any effect, because remember, we have this, that the areal density is cross-section time, sorry, the reaction rate is areal density times cross-section as the rate. Okay, so you need a pretty thick hunk of reflector to make this work. And that's it. Amazingly, we got to the end of this. I know this was rather a lot, okay? So if you raised your hand bravely or now simply evolved that braveness, okay, you can go ahead and send me an email and tell me roughly when you would be available for an open-ended Q&A. It probably will have to be in meeting. My guess is it will not work at the same time for everyone, okay? And depending on how that goes, I'm happy to hold another one. Okay. All right, thanks, folks.
Someone turn their homework in without a name on.